Hello, welcome to Oracle Developer Live. I'm Siva Idupaganti. I'm joined with me by Somnath Lahiri. We both are responsible for OCI's core messaging services. Today, we're going to talk to you about building a cloud-native e-commerce application using modern messaging services. Our agenda today will go over the common messaging choices that are available when you're building these applications. And then we'll talk about a specific application called the on-demand food delivery application. We'll go over a couple of use cases and the corresponding architecture that is necessary to support that. And then we'll dive into demos for a couple of these use cases. And then we'll end with a Q&A. We have a safe harbor statement just to indicate there may be some future-looking services. We'll clearly indicate when some service is not generally available. So when you think about modern application building, everyone thinks about microservices-based architecture. It's so widely used and sworn by developers across the world. There are several benefits to using microservices-based architecture. And when you think about what means in a microservices architecture, there may be several definitions, but it effectively boils down to a style where the application is structured using loosely coupled services. When you think about how these different services talk to each other, there's a producer and there's a consumer, and they use a message in between. The communication between these producers and consumers, there are two major models: a synchronous communication model and asynchronous communication model. In the synchronous model, the producer produces a message and waits for the consumer to process and respond before the producer can proceed forward with its logic. This is typically observed in a client-server-based architecture where you have HTTP APIs, especially when you're talking about REST API-based applications. What this does is it creates a tight coupling between the producers and consumers. Any increase in traffic spikes would require the consumer to be able to handle that load. And if the consumer is unavailable, or if there is a high latency, it impacts the producers too. When you think about the asynchronous communication model, there is a producer produces a message and then proceeds forward without waiting the response from the consumer. For example, if you think about a modern reservation system, the producer may accept a booking and it stores that in a durable message queue and proceeds forward to accept new requests. And then the consumer comes on, processes the messages from the queue. This provides a very loose coupling between the components of the application and has several benefits. The traffic spikes that we talked about before, the latencies and the availability issues are gone when you use this asynchronous communication model. So going back to the benefits of microservices, if you really want to achieve independent development, deployment, and maintenance of your microservices and independent scaling of these microservices, an asynchronous communication model is significantly important. And when you think about the asynchronous communication, there are three main channels. You have streaming, which is used for real-time message transfer. And you have multiple consumers that read and process the messages in the order as they were delivered into the stream. The next one is a queue. You can think of it as a durable message buffer. You can receive messages. The producer produces the message to the queue, and there could be multiple consumers who are trying to process messages in the queue, and they could be connected to the same queue. And then you have the pub/sub model, where you have, this is a fan-out model, where you have topics and subscriptions. A message is published to a topic, and there could be multiple subscribers for the topic which receive that message. OCI offers open standard-based, scalable, reliable, and serverless services for all these different communication channels. You have OCI streaming, which is used by thousands of enterprise customers to meet their real-time communication needs. The OCI notification service provides a pub/sub model and allows to integrate with third-party applications, and it has been in production for several years. OCI queue service is currently in limited availability, and we're looking forward to expanding access to more customers. I'll now hand it off to Somnath to take you through the architecture of a food delivery application, the key characteristics of the communication between these microservices, and the appropriate communication channel you want to use. Over to you, Sumna.
Thank you, Siva. We are talking about the on-demand food delivery application. I'm super excited to talk about this app. Now, this app, many of you have used it. It's similar to Uber Eats, DoorDash, Grubhub in the US, and there are many other applications around the different parts of the world. If you think about a food delivery application, there are three parties involved: customers, restaurants, and the delivery partners. So some of the key use cases are, or the core use case is, customer places the order, they choose menu items. When they places the order gets to the restaurant fulfills the order, and whenever the food is ready, the delivery partner fetches that food from the restaurant and finally delivers to the customer. So that's the whole cycle of the key components of the use cases for a food delivery application. Now, let's take a look at how the architecture might look like. Before we go into the architecture, I just want to caveat that this is just a representative one. We haven't just laid out the entire architecture. There are so many other components. But if we focus on the core components, there are fundamental 4 building blocks. Number 1, the UI components through which the customer, the restaurant, and the delivery partners interact. And then there are the whole suite of the backend applications. And these applications are installed and resourced in Oracle Cloud Infrastructure region. So the first set of that is all the API access and authentication part. We have Internet Gateway, API Gateway, Auth and Auth0 as part of the Oracle Cloud Infrastructure. The second component of it is the microservices, which are deployed as the container you get for Kubernetes, and the related interaction between those, which is achieved by the messaging services. And finally, we have a persistence layer, which can be an autonomous database, which is used to store all the information. Now, what we'll do, we'll take few example use cases and go deeper into the requirements of those. Let's just see how does it look like. We are going to talk about the order processing system. On a very fundamental level for a food delivery application, there are different microservices. Let's start with the order receiving microservice. So this service, what it does, it takes the order from the UI components, through the API gateway. It communicates with the payment system just to make sure that the customer's financial instrument is valid. Then it hands off the information to the order processing microservice, which in turn routes the order to the respective restaurant tab. Now let's focus on or zoom in the communication between order receiving microservice and order processing microservice. What are the key requirements? And then we'll see which messaging application is the right choice for it. Now, for these applications to communicate with each other, it has to be a non-blocking nature. What it means that if for any reason the order processing microservice can't process a customer order, it should not block other orders. The order which did not get processed for the first time, the messaging system should be robust enough to re-deliver the same order again to the order processing microservice. In addition, these applications should be decoupled. That means if for any reason the communication gets broken between these two services, we still should be able to receive the orders from the customer. And finally, the system would be robust enough to handle scale and workload spike. Think of the thousands of orders which are coming in during the lunch and dinner hours. And finally, there should be a robust error handling mechanism in there. So if for any reason a order can't be processed, there should be some provision like dead letter queue where developers can go and see if there is anything wrong with those particular orders. Now, if we combine all these requirements, messaging queue is the ideal choice for a messaging application for communication between the order receiving microservice and the order processing microservice. Now, let's look at some of the sample code. So in a message queue, it's a durable message buffer. Whenever we push a message to the queue, it's durably persisted in there. So we are showing the sample code base to create the queue. So this is part of the administrative process or admin work or the control plane work where we go and provision the queue. And there are other components, the producers or the order receiving service, which is producing orders to the queue, and the consumer, which is the order processing service, which is taking the order or pulling the order from the queue. Let's look at the code base for the order receiving microservice. So we provided a sample order JSON. As you can see, we have the customers are capturing order ID, items, customer ID, the customer location, their lat long information. So this is a single message. So this is what the message is consisted of and what the producer is pushing to the queue. And we have shown some sample producing to the queue code. As you can see, you can push one message or you can create an array list, create a batch of messages and put one request to the queue. And similarly, on the consumption side, there are two components I want you to focus on. Number one, the consumer gets the order from the queue. After it's done processing, that communicating with the restaurant app and routing that information to the respective restaurant app, it deletes the order from the queue, just to make sure that the same order does not get processed multiple times. So that's why it's called the competing consumption model, where multiple consumers are trying to take message of the queue. So I hope it gives you a fundamental understanding of how a queue works, what are the basic components. Now let's roll and see a demo of the order processing application. We'll switch back to terminal in order to show the demo. So for this purpose, I already created a queue in one of the Oracle Cloud Infrastructure region. So let's go ahead and get the details of the queue. So as you can see, it's created in our Ashbound region. There are three other parameters I wanted to focus on. The retention, so which defines if a message is not consumed by the consumers and subsequently deleted, the message will stay in the queue for a period of 1 day. Then the second one, the visibility timeout. So once a consumer gets the message from the queue, it will become invisible to other consumers for a period of 20 seconds. So a message doesn't get processed multiple times. If for any reason the queue does not hear back from the consumer, maybe the consumer dies or some network failure happens, the message will again reappear in the queue after 20 seconds for other consumers to consume that message. The third one, the dead letter queue delivery count, which is measured, say, if a message does not get delivered or can't get processed by the consumers after 3 trials, 3 attempts, the message will automatically move to the dead letter queue. Now let's go ahead and look at the application. Say this is the order receiving or the producer application. So we are going to produce or create some messages in the queue. Say it's in the morning, we don't have that many orders coming in, it's slowly trickling in. We are producing 2 messages to the queue. At this point, if for any reason the consumer applications are not running, the connectivity is broken, still the message gets durably persisted in the queue. Let's go ahead and see the statistics of the queue to understand the details. So as you can see, in queue, the 2 messages got durably persisted. So for each message, there are 3 replicas which are created, and those are stored in 3 different nodes. Now we'll start one of the consumer application, which will go ahead and try to consume or try to get the message from the queue. So we'll use the get message API in order to interact with it, and we'll get one message from the queue. So it gets one message from the queue. However, say this can't process the message. For some reason, this consumer dies, and it can't process the message. Now, one of the key requirement is we had is it should be non-blocking in nature. So non-processing of one message should not block other orders because we want the system to be as smooth, as efficient as possible. So the other consumer comes up and it tries to get the next message. So as you can see, the ID or the message ID is different. See, it got the next message. It's success. It's now this consumer is able to successfully process that message. It routes this order to the corresponding restaurant, and it's ready to say, "I'm done processing this message." So after successful processing of it or routing of it, it deletes the message from the queue. And we use the receipt ID. So receipt ID is unique for each message in the queue through which the queue service understands how the consumers are interacting with it. Let's look at the statistics. So this message is still available in the queue. Now, this consumer comes back again. It's trying to process this message. So as you can see, the delivery count of this message increases by 1. Now, even after getting the message, this consumer dies again. So I have my second consumer, which now goes and tries to get the message from the queue. So it will become invisible for a period of 20 seconds, but after that time, it will again reappear in the queue. And so this message can reprocess that same message. Now, say this consumer is again trying to do it, but for any reason there is something wrong in the message. So as we defined in the dead letter queue, that if the message can't be delivered after 3 delivery counts, automatically it will move to the DL queue or the dead letter queue. As you can see, the dead letter queue count has increased by 1. So that's the default error handling functionality that queue service provides. Now, say it's the lunchtime. Now, instead of few customers, there are hundreds of customers who are placing orders to our order processing system. So let's create a bunch of orders and then see what is happening with the queue statistics. Yeah, the number of messages is going up, my queue size is going up. So what I can do at this point, I can consume these messages. And instead of consuming one message at a time, I'll try to consume in a batch of 20 messages. However, this consumer is consuming the message slowly. It's still building up. There are a lot of orders which are coming in. You can see, let's look at the statistics. Yeah, there are in-flight messages 14. That means this consumer is trying to process it. However, still there are a lot of messages in the queue. It could be as many as like few million messages in the queue. So in that stage, I spin up another consumer, which is also starting to consume message from the queue. So I can add as many consumers as possible. So that's the beauty of queue. A number of consumers can simultaneously process messages from the queue. So that's how it guarantees parallel processing of data. So, we focused on the scale part, which was the last set of the requirement we had for this order processing application. I hope I was able to convince you why queue is the ideal choice of messaging system for the application. So hopefully so far we are able to prove that queue is the ideal choice of messaging system for this kind of use case.
Why would we not use streaming for this use case? Can you help me understand that more?
Sure. Yeah, I have seen this question come up that the developers are acquainted with a specific messaging system, say they are using streaming or Kafka, and they want to use it for this use case. It can be used. However, there is a lot of complexities because in the streaming, it does not provide you to out of this box functionality of message voice processing. So it helps you fetch a group of message, and if one of the message fails, then the developer has to create a mechanism for which they are creating another stream. So for some reason, some of the messages did not get processed. They push that message to the retry stream. And similarly, they have to create a chain of retry streams. However, in queue, all these error handling functionalities is provided out of the box through the support of dead letter queue, as well as multiple consumers are trying to consume the message from the same queue. So streaming can be used. However, it's much more intensive in terms of development and maintaining that solution. So I would highly encourage to use queue for this use case.
Awesome. I would obviously want to spend more time on my business logic and not have to handle the error scenarios. If the managed service can do it, that's the best. Also, what metric would indicate the need for more consumers? I see that you showed 2 consumers. When would you add third, or the end consumer?
Yeah, that's a great question. So one of the metric we could look at is the length of the queue length. If the queue length increases, that means the producer is hammering the queue with a lot of messages. I mean, which may happen during the peak hours or the rush hours during lunchtime, dinner time. So you'd look at that metrics, and depending on the threshold, you want to spin up other consumers so it can go ahead and process the messages. Also, you can increase the size of the batch size. So instead of consuming one message at a time, the consumer can consume multiple, say 20 messages at a time. So these are the 2 ways the developers can monitor and make sure that the consumers are up to date.
Fantastic. Thank you.
All right. So Shiva, if you're done with your questions, let's look into another use case. This application, we are talking about the event data. As we may know, the ordering system, an order goes through multiple phases. At first, customer places the order, the restaurant accepts the order, the delivery partner goes and fetches the order from the restaurant, and finally it gets delivered to the customer. Now, as you can see, there are multiple services which is working on an order, and they need to emit these events somewhere. And on the consumption side, so as they're emitting the events, as you can see, there are hundreds of thousands of orders, and the number of events is even more. So we need a messaging system which is able to handle the throughput, all the throughput which is coming to the messaging system. On the consumption side, we have the different microservices such as tracking service, which provides the capability for customers to track the orders. Restaurant service, which is also fetching the orders to get an understanding of where the delivery partner is. And finally, we have other processes like we could use push this data to durably persisted in autonomous database. Maybe we can use a Kafka Connect. As well as there could be a batch processing for audit purpose. I want to run a batch process to see what is the efficiency of this whole operations process. So on the consumption side, there are multiple class of application which needs to consume the events from this messaging system at their own pace. And some of the applications read data at different intervals. Maybe the batch applications runs once in 2 days, once in 7 days. So we need a messaging system which stores the message durably for a period of time, and multiple consumers can read at their own pace. And if we zoom in on the tracking service, all the orders with a specific order ID need to be in sequence. So whenever we are opening the app and seeing where my order is, I should see a clear sequence of events that happens. So with the specific order ID, all the orders need to be in sequence. Now, if we combine all these requirements, the streaming service is the only one which fits all these requirements. So streaming is the ideal choice of messaging system for this use case. Now, let's go ahead and let's take a look at a demo. We'll look at the code base at first to give you the context, and then finally we'll run the demo. Similar to queue, a stream also has 3 components. The stream, which is an append-only log. On the one hand, there is the producer, which is producing events to the stream. On the other hand, there is a consumer, which pulls the records or pulls these events out of the stream. The great thing about Oracle streaming is it's Kafka compatible. we are going to interact with stream using Kafka API. So let's take a look at this Kafka admin API through which we'll create the topic of the stream. At first, we are creating the connection string, and then we are calling the create topic method. In create topic, one of the parameters we are passing, which is the partition count. A partition is the single atomic unit of a stream. A stream can have one partition to as many partitions as you may want, depending on the application throughput. On the producer side, we have this Kafka produce API through which we are interacting, which in turn is calling the send message method. In the send message, we are passing the key value pair. So key is the partition key through which streaming ensures ordering guarantee. We'll take a look at this method in detail during our demo. On the consumer side, it's calling the Kafka consume API. And one thing to note here is the CG name, which is the consumer group. As I said earlier, streaming ensures multiple applications to read data at its own pace. So through the concept of consumer group, it ensures that the downstream application can read the data at its own pace. Let's look into the actual demo. Here, there are multiple tabs which are open. Let me just make it a little bigger so it's easier to see. At first, we'll start with creating a stream. As you can see, I'm creating a stream with partition count 3. Let's execute that command. Again, I'm interacting with the streaming service via Kafka API. So I've created the order events. This particular topic or stream, as we call it, our streaming parlance. Now let's look at the producer data. So what we are doing is this is the order receiving service. As soon as the order comes in, customer places an order, this particular microservice emits an event to stream. What we'll do here is we'll provide the data, say customer placed the order. So that's the metadata we are passing. Now let's create few order with this metadata. So say order ID is 100, then the next order ID is 101. We are also passing the same metadata. Another order ID is 102. Similarly, let's create another order. Now, as the order passes through the order processing application and the restaurant accepts the order, it also produces an event to the stream. So let's start this producer as well. Now what we'll do is for the same order ID, however the metadata is different here. Here the metadata would be restaurant accepted the order. So with this metadata, we'll create a couple of records which were captured from the order receiving service. So similarly with the 101, I'm passing this metadata. Let's create a few more records. I think that's good enough. So now, as the order passes through these different services, they are emitting the events. Now let's try to consume these events. So we are going to the order tracking system, which is fetching the order, which is pulling the order from the stream. So as you can see here, we are creating a consumer group called tracking, since this tracking application is accessing the order. So let's see what tracking does. So it's pulling all the records from the stream. As you can see, all the records with a single key went to the same partition. So order with order ID 100, that went to partition 0. Similarly with offset 0, and similarly order ID 102 went to partition 0. So by which, keeping the same order ID or the same partition key, we could ensure that all the events pertaining to that order goes to the same partition. And when the consumer is pulling the data, it's always in sequence. Now, you may ask, okay, what about the tracking system? Or what about the other consumer groups or disparate consumer application? So for this, let's take a look at that. We are creating another consumer group. The name of the consumer group in this case is the Kafka Connect ADB, so autonomous database. So this consumer group is taking data from the stream and pushing it to autonomous database. As you can see, the other consumer group has already consumed all the data at that point. Now this autonomous database, this particular consumer group is again consuming the data, but at its own pace. Like it's accessing the same data. The data is not getting deleted from the stream, what we saw in the queue. Because in the queue, once a consumer accessed the data and processed it, it got deleted from the queue. But in the stream, the data is persisted. It's an append only log. So each consumer group can access the data at its own pace. Now let's start another consumer, which is pertaining to the consumer group tracking. Let's start this thing. Now it doesn't have any record to fetch at this point because the other consumer has already fetched all the records. Now what we'll show is, during certain time there are a lot of events which are coming in. So I'm going to spin up a bulk producer which will produce a bunch of data to the stream. And let's see how the work is being distributed between the two consumers which belong to the same consumer group. So I produced a bunch of events to the stream. Let's see what is happening with the this particular consumer. So this belongs to the consumer group tracking. So as you can see, it's only fetching the order from, or the events from partition 2. And the other one, which is fetching the order from partition 1 and partition 0. So there is a consumer coordination which is happening, and the order work is being distributed among two consumers. So with this, I hope we are able to establish the point why streaming is the ideal choice of messaging use case. Now let's switch back to the actual presentation.
That was a cool demo, Somnath. When do you think there should be more consumers that should be reading from that stream?
For that, we need to look at a metric, consumer lag. So if the consumer is falling behind from the number of messages which is available in the stream, we need to add more consumers. However, in a stream, as I said earlier, there is a maximum number of there is a limitation on how many consumer can be added. At a time, a consumer can read from one partition. So the maximum number of consumer would be equal to number of partitions in the stream.
Perfect. And when you think about partitions, how do we know when to add more partitions? Is this something that I have to think about it as a developer?
Yeah, this is what you have to think about as a developer. So as I said earlier, partition is the single atomic unit of a string. A partition can accept 1 megabyte per second of ingress data, ingress throughput. So whenever you are seeing that from the throttling matrix that we provide, if messages are getting throttled, that's the time to add more partitions to your stream.
Perfect. I think I don't have any other questions for this demo. Let's move on to some questions from the audience. I see here a pretty interesting question. I have a Kafka implementation. How can I migrate to using OCI's services?
Migration from your on-prem Kafka to OCI is super simple. And we have built the OCI streaming service and its Kafka compatibility, keeping that in mind. All you have to do as a developer is changing the connection string. I showed in my demo that building the connection string is super simple. So instead of pointing to your Kafka implementation on-prem or in some other cloud, you just need to change the connection string to point it to our OCI regional endpoint in which we are deploying the application. So overall, it's super simple.
Perfect. So once the data is ingested into a stream, what are the different ways in which the data can be consumed? Another interesting question, Sona.
Yeah, there are a couple of ways. I just focus on 3 key ways. Number 1, you can use the GET API. You can interact with our native GET API for streaming or Kafka. The second option is you could use Kafka Connect. So that's where the ecosystem of Kafka comes in. There are hundreds of connectors which are available on the production side as well as on the consumption side, which provides the ability to push data to a stream, as well as on the consumption side to take data out of stream to multiple other downstream applications. And finally, the third way, we also provide a native way to take data out of streaming. So we have a support for Service Connector Hub. So Service Connector Hub is a fully managed serverless connector through which you can take data out of streaming and push it to multitude of other downstream Oracle applications. For example, for the use cases like you need to take data out of streaming for long-term archiving, you could do that via integration of streaming with object storage. You need to fire some serverless functions based on some data. You could do that via streaming and functions integration. And there are a few other integrations which is available there. I'd highly encourage all the developers to go and check out the Service Connector Hub. Now, in addition to that, we have the stream processing functionality. So before taking the data to the downstream application, the developers have the ability to fire functions and work on the content of the stream before taking it to the downstream applications. So if you have to enrich the content or you have to route data based on certain logic, you can certainly implement all those application logic in Oracle functions. There are multitude of ways, and we are adding more connectors in the future. Stay tuned. A lot of more exciting things are coming in streaming.
Awesome. I see another question related to security. How would I secure my data processed by the OCI's messaging services?
Yeah, as an enterprise cloud company, which is our sole aim is to focus on security. And we achieve it via two ways. Number one, access level security. Number two, data level security. For access level security, we have integration with OCI, Auth-in, Auth-Z service, authentication authorization, as well as the permission management. In addition to that, especially streaming has integration with private endpoint. That means a streaming endpoint can only be accessible from all the consumers or clients within a customer's VCN. So we restrict the traffic this way. Let's move on to the data level security. We encrypt all the data in motion as at rest. So at rest, by default, we encrypt all the data by Oracle managed keys. Our customer also has the ability to bring their own keys, maintain the keys in OCI vault, and through which it's ensured that the data is always encrypted.
Perfect. There's another question related to semantics of how the data is accessed from the services. What's the difference between the at least once and exactly once processing?
Yeah, this is an interesting question. So delivery semantics of at least one means this messaging services is delivering the data on the consumer, or consumer can pull the data at least once. It may happen that the data is sent there multiple times, more than once. And exactly once ensures the data goes to the consumer system exactly once. For example, in our application of order processing, we want to make sure that restaurant finally gets the order only once. I mean, it's great for customers. If it goes twice, they would get the same order multiple times, but it's not good for any of the companies which is building the application. So our recommendation would be to build the exactly once functionality on the downstream consumer level. So the logic could be, if an order ID or transaction ID, it already finds it in a key value pair database, which is maintained on the consumer side, drop the order. If it is not there, then place the order to the restaurant application and make an entry into the key value pair database. So finally, our recommendation is to build the exactly one functionality on the downstream consumer level.
Perfect. Another question related to the delivery or an access model. When do you use pull versus push model?
Yeah, so there are various ways customers or developers can tackle this particular part. For example, in streaming and queue, we implement pull-based semantics. So consumers pull messages from the stream or queue. In case of Oracle notification service, it's a push-based semantics. So whenever a message comes in, it automatically gets delivered to the subscribers, which is subscribing to this messages of the events. Now, ideal recommendation is to implement pull-based when you have to scale the number of messages. So you don't have that many consumer application downstream, and they are trying to access the data from the stream or the queue. Whereas if there are multiple number of subscribers for which you need to send this information, use the push-based model. For example, in our restaurant management order processing application, finally order processing application had to take the data and push it to the respective restaurants, depending on in which restaurant the consumer has placed the order to. One way of implementing that is to have one queue for each restaurant. However, that's not the right way of implementing it. The actual way of implementing, or ideal way of implementing this would be to have multiple topics and subscriptions. So each restaurant has their own topic and the subscribers are listening for it. So whenever an order comes in, then only the final restaurant tab will get notified about this. So, there are a lot of nuances on when to use push versus pull, but, on an overall level, this would be a guidance, it looked at very thoroughly depending on the application use case.
Perfect. That will be our last question that we would take in, given the time. Let's move on. So Somnath, you talked about the application all through and went through different use cases within the application. Here are the design principles that Somnath has used when he's building the application. This is part of the broader effort to define design principles that are available on OCI Architecture Center. We encourage all the developers to take a look at this Architecture Center and specifically the reference architecture, reference design principles that will help you build scalable, secure, and production grade applications on OCI. Going to the next slide. Here are, if you haven't already known, OCI provides the best world-class free tier, which will allow you to try out OCI cloud services and start building your applications. So get started, go create an Oracle free tier account, and you could access a lot of resources that are available for you on developer.oracle.com.